was a typical evening in southeastern Nebraska. Folks went about their work and their pleasure as usual. Just another evening, the same as the night before. So far as they could tell, for example, there was nothing different about the source of the electricity that lighted their living rooms, that cooked their dinners, that powered their television sets, that pumped their gasoline, that performed 101 other duties to make their work more efficient, their lives more enjoyable. But there was a difference in the source of that electricity, a significant difference. For the first time in Nebraska, that electricity was being produced by nuclear energy. The nuclear power facility at Hallam, Nebraska, a 240,000 thermal kilowatt sodium graphite reactor capable of producing 75,000 kilowatts of electricity, was on the line. Located on a 600-acre site 20 miles from Nebraska's capital city of Lincoln, the Hallam Nuclear Power Facility looms up in startling contrast to the surrounding farmlands. The complex of buildings includes a reactor wing, turbine-generator wing with conventional electric generating facilities, an administration wing, cooling tower, waste storage building, and substation. Overall size of the reactor wing is roughly 116 feet by 275 feet. The plant was designed with prime consideration for safety in the handling of radioactive waste materials in the unlikely event of an accident. The Hallam nuclear facility was built jointly by the Atomic Energy Commission and Consumers Public Power District of Nebraska, and will be operated by consumers under the AEC's Power Demonstration Reactor program. One objective of this program is to advance the time when the cost of nuclear power will be reduced to levels competitive with power from conventional fuels. Another important objective is to advance the state of nuclear reactor technology in general. The specific objective of the Hallam project is to demonstrate the economic and technical practicality of a central station power plant using a sodium graphite reactor. This will require operation of the plant for the primary purpose of producing the maximum amount of electric energy. It is anticipated that operation of the Hallam facility will provide knowledge and experience that will lead to the realization of competitive nuclear power in subsequent reactor plants. The Hallam facility is one of a family of reactors which have demonstrated the technical advantages of liquid metal coolant. The others include the experimental Breeder Reactor 1, which in 1951 produced the first electricity generated with nuclear energy. The experimental Breeder Reactor 2. The privately financed Enrico Fermi Fast Breeder Reactor. And the sodium reactor experiment. The SRE, in which the technical feasibility of the sodium graphite concept was demonstrated, was built and operated for the AEC near Los Angeles, California by Atomics International, a division of North American Aviation Incorporated. As a result of this experience with the sodium reactor experiment, Atomics International was assigned the overall technical responsibility for the design of the Hallam facility. Construction of the Hallam facility was authorized in 1957. The plant site was chosen on the basis of Nebraska's population and power load center and the availability of land, water, and transportation facilities. Groundbreaking ceremonies on a gently rolling hill typical of the surrounding terrain were held on June 28, 1958. In a conventional steam power plant, heat released by the combustion of fossil fuels, oil, natural gas, or coal, is applied to high-pressure boilers to produce the steam that turns the turbine generator. In the Hallam nuclear power facility, atomic fuel is substituted for the fossil fuel in the production of steam. At Hallam, Conventional fossil fuel facilities constructed by Consumers Public Power District have been integrated with the nuclear facility. The conventional boiler and auxiliaries with the turbine generator, now operated as part of the nuclear facility, were installed by consumers to supply generating capacity needed in advance of the nuclear facility's completion date and during the period of reactor test operation. The conventional facility was designed to match the reactor steam conditions of 800 pounds per square inch of pressure and 825 degrees Fahrenheit temperature. The two facilities, conventional and nuclear, have centralized control, so integrated that the turbine generator can be operated automatically using either source of steam. After completion of the reactor test operation, it is planned to release the fossil fuel boiler from the system for use with a second generating unit which may be built later on the site. The heart of the Hallam nuclear facility is the reactor core. The fuel is a metallic uranium element contained in stainless steel tubes which are suspended in clusters within the core. Moderator elements made of graphite blocks surround the fuel elements. Liquid sodium serves as the coolant and heat transfer medium because of its high boiling point and excellent heat transfer properties. Starting at the bottom of the reactor vessel, the sodium flows up past the hot fuel elements to an upper pool, and then out of the vessel at the top at a temperature of approximately 950 degrees Fahrenheit. The primary sodium coolant becomes radioactive during its passage through the core. This radioactive sodium is pumped through 3 identical primary loops to intermediate heat exchangers and returned to the reactor vessel at approximately 600 degrees Fahrenheit to repeat the cycle. The heat carried by the sodium in the primary loops is transferred by the intermediate heat exchangers to the 3 secondary sodium loops, which are non-radioactive. The heat from the secondary non-radioactive loops is utilized in 3 steam generators, producing the steam that turns the conventional turbine generator. With installation of the reactor core cavity liner scheduled as the first major objective, full-scale construction activities at the plant site began early in 1959. The reactor building excavation was 80 feet deep at its deepest point, the point where the maintenance cell is installed. Reinforced concrete floors were built up to a thickness of 4 feet. Poured reinforced concrete walls are even thicker, up to 6 feet in some places. The stainless steel reactor core tank, 19 feet in diameter by 33 feet in depth, is surrounded by a thermal shield. An outer tank, a layer of thermal insulation, and the reactor cavity liner, which is made of half-inch carbon steel. Steel pipe welded to the outer surface of the reactor cavity liner provides a means of circulating demineralized water to remove heat from the surrounding concrete. A pipe gallery accommodates sodium inlets and outlets to the core tank. The reactor cavity liner is surrounded by a reinforced concrete, which provides a structural support as well as a radiation and thermal shield. The upper 6 1/3 feet of the adjacent wall is made of high-density concrete. In the bottom of the cavity liner, individual columns 2.5 feet high and 1.5 feet in diameter were installed to provide support for the outer vessel. Fabricated in Philadelphia, the reactor core vessel and its outer tank were transported by waterway to Plattsmouth, Nebraska. To accommodate the overland movement of the huge vessels, it was necessary to widen and strengthen bridges and move utility lines. The outer vessel, shown in this model, is 20 2/3 feet in diameter and 36 feet high, and was fabricated from half-inch thick low-alloy steel. The outer wall of the outer vessel is covered by a 12-inch layer of thermal insulation, made up of individual blocks of asbestos fiber. The insulation serves to hold the heat within the reactor, thus adding to overall efficiency. The insulation also protects the surrounding concrete from high temperatures. The bottom of the outer tank supports the core tank as well as the thermal shield. The thermal shield, which surrounds the core tank, was made of 2 concentric rings cast from low-carbon steel. Their function is to absorb most of the heat due to gamma rays and neutrons. Each cylinder is formed by a series of 10 adjacent vertical curved plates, which rest on the bottom of the reactor outer tank and are 33 1/3 feet high. The reactor vessel is made of stainless steel 3/4 of an inch thick, except for the base and the areas of the inlet and outlet sodium nozzles, which are 2 inches thick. The bottom was formed cold, and the sides were built in successive ring sections, each welded in place. A dome-like containment shell used with some nuclear power plants is not required for the Hallam reactor because the sodium coolant is not under pressure. The reactor vessel and the primary sodium system are surrounded by a series of steel-lined concrete cells. These nitrogen-filled cells would prevent the escape of radioactive sodium vapor or fission product gases into the atmosphere and radioactive liquids into the surrounding subsoil. 3 main sodium inlet nozzles are located 28 inches above the base, and 3 sodium outlet nozzles leave the vessel 23 feet above the base. At the top, a stainless steel bellows assembly seals the reactor vessel to the upper cavity liner to prevent sodium vapors and the helium cover gas from escaping. Within this vessel, liquid sodium flows through the core at the rate of 21,600 gallons per minute. A stainless steel grid plate is supported 42 inches above the bottom of the core tank by individual columns and a support ring. The grid precisely locates the moderator elements with relation to the fuel elements. The moderator elements consist of logs of graphite sealed in stainless steel cans. The function of the moderator is to slow down neutrons released during atomic fission to increase the probability that the neutrons will initiate further fission and thus sustain the controlled chain reaction. The graphite logs, 6 to a can, were machined into a hexagonal shape. The stainless steel sheath material forming the sides of the can is 16 1/1000 of an inch thick. The sheath is made up of 2 formed panels welded lengthwise. The base of the element is 1/2 inch thick stainless steel casting, which includes the 6 inch high pedestal supporting the moderator element on the bottom grid plate. Spacers maintain a 16 1/100 inch clearance between moderator elements. In addition, core clamps are provided on the internal vessel wall to hold the moderator elements in place. The clearance between the elements permits the circulation of small amounts of sodium to cool the graphite. To avoid contamination, components were continually cleaned during installation to remove lint or other foreign matter. With the moderator assembly in place, the huge top shield, weighing about 300 tons, was placed over the tank. 6 feet thick, the shield is filled with lead and dense concrete and provides radiation and thermal shielding directly above the reactor core. The shield can be rotated and has removable plugs which extend completely through the shield. These plugs permit access for the installation or removal of fuel and moderator elements. Each fuel element is made up of individual rods of 3.6% enriched uranium molybdenum alloy. The rods are approximately 6/10 of an inch in diameter and 13 1/2 feet long. They were assembled by inserting 3-inch to 12-inch length uranium slugs into the stainless steel jacket. These uranium slugs were cast to size, and after cleaning, the materials were subjected to tests to assure quality. The slugs were then cut to usable lengths, and after again cleaning the material, it was ready for insertion into the stainless steel container. The space between the inner wall of the jacket and the fuel slugs was then filled with sodium to improve the transfer of heat from the uranium fuel to the jacket. After quality control tests were completed to ensure the integrity of the assembly, the stainless steel jacket was capped, sealed, and welded. 18 of these rods were then assembled in a bundle, supported at the top and bottom by a bracket, and the assembly then inserted into a zirconium process tube. At the upper end of the process tube, there is a variable orifice which is used to control the amount of sodium flowing over the fuel element, and in this way regulates the operating temperature of the fuel element. A continuing program of testing assured that the work was being conducted to meet the rigorous specifications. Reactor control is maintained by 19 combination regulating and safety rods inserted down into the reactor core. Each rod is made up of rare earth oxides which absorb neutrons. Each rod is positioned within the core by a motor-driven gear reduction unit mounted on a carriage over the reactor core and is held to the drive motor unit by an electromagnet. Any malfunction would interrupt the power to these electromagnets, and the rods would then drop into the core to shut down the reactor. During the shutdown periods, the neutron absorbers stay in the core, and the disconnected overhead carriage is removed to provide easy access to the face of the upper shield. The use of an intermediate heat exchanger is required because the sodium becomes radioactive in passing through the reactor core. Each intermediate heat exchanger is made up of 2 units operating in parallel. Each unit is of the shell and tube counterflow design, with the primary sodium contained in the tube side. The stainless steel exchangers are mounted vertically in the heat exchanger cell. Thermal expansion is provided by a bellows mounted in the straight shell section and permits solid construction of the tubes containing the radioactive sodium. In the intermediate heat exchanger, the secondary loop of non-radioactive sodium is heated by the primary sodium to 895 degrees Fahrenheit. The hot sodium is pumped by centrifugal pumps to the 3 steam generators. These pumps are similar to those used in oil refineries. Each steam generator consists of an evaporator, moisture eliminator, and superheater. Construction is of the shell and tube type, using double-walled bayonet tubes to prevent leakage between sodium and water systems. The bayonet tubes utilize helium between the 2 walls as a monitor for leaks. The evaporator is a kettle-type design, with the water carried in the shell. The moisture eliminator delivers dry steam to the superheater. Steam piping connects each of the 3 steam generators to the main steam line, and the 825 degree Fahrenheit, 800 pounds per square inch steam is fed to the turbine generator. After the steam passes through the turbine, it is condensed to water and returned to the individual steam generators at 325 degrees Fahrenheit. High-grade superheated steam is produced by the liquid sodium heated generators. The turbine generator is basically of conventional hydrogen-cooled design. While rated at 100,000 kilowatts, it will have an output of 75,000 kilowatts in the initial reactor operation. It was actually put on the line the spring of 1961, operating with the conventional steam facilities. The substation uses a single transformer to convert the 13,800 volts of the generator to the 115,000 volt transmission lines, which distribute the power to the eastern 2/3 of Nebraska. Auxiliary transformers supply power to the plant for internal use. In January 1962, the plant was ready for preliminary testing of nuclear equipment. It began with a dry critical test. The installation and removal of the fuel elements is handled by a fuel handling cask, heavily shielded by lead against radiation. The 55-foot high chamber is supported by a gantry crane. When a fuel element is to be changed, a fresh element is picked up from the storage area. The cask is then moved to a position above the reactor. An indexing mechanism moves the cask to a preset position precisely in line with the given fuel element. A pneumatic mechanism forces the lead radiation shield down onto the surface of the loading space. A gas-tight seal is made. A pickup device within the cask is lowered to engage the shielding plug of the used fuel element. The plug and spent fuel element are lifted out of the core as one unit. A revolving fuel support plate at the top of the cask is then rotated 180 degrees to position the new fuel element over the empty fuel channel in the core. The new fuel element and plug are lowered into place. The cask then carries the used fuel element to a storage cell, where the radioactivity is allowed to decay for a period of 60 to 90 days. Then it is moved to a cleaning cell, where it is steam cleaned and rinsed to remove any sodium adhering to the outer surface. From the cleaning cell, the fuel element is moved to the maintenance cell, where the fuel rod bundle is removed and prepared for shipping to a chemical processing center. The water that has been used in the cleaning cell is transferred from the cleaning cell to a radioactive liquid waste system where it is held in large tanks. The contents of these tanks are analyzed for radioactivity, and if there is any significant radioactivity, the contents are treated to remove the radioactivity, and the residue is then packaged for shipment to waste disposal sites. If, however, the contents are free of significant radioactivity, the water is allowed to seep into the ground at the plant leaching field. This same method is used to analyze any liquid that might be radioactive, even the water used in the plant laundry. This conservative program is further supplemented by a continuing program of radiation monitoring in the plant, as well as the monitoring of the air, soil, plants, and water which make up the environment of the plant area. As each system was completed, operating personnel started a program of test operation, which assured that the equipment would perform satisfactorily under both normal and abnormal conditions. As an increasing portion of the plant was completed, this testing program was expanded until the entire plant was ready for insertion of fuel. In January 1962, the reactor was placed in operation for the first time in dry critical tests. Wet critical low-power tests were started in August 1962. These low-power tests provided further assurance that the plant was operating satisfactorily, and a period of about 9 months was used to carry the testing program through to its full power operation. The inherent safety of the plant was proved as the reliability of the control and safety equipment was determined and verified with each increase in power. This safety program, which was started with the conception of the plant, included inspection of individual components as they were being fabricated, and was carried through to a detailed safety analysis of the completed plant. Emphasis on the safety program will continue throughout the period of plant operation. In 1963, electricity produced by nuclear power began flowing through the substation. The Hallam nuclear power facility was on the line.